In this lecture, I'll be talking about artifacts in functional connectivity MRI and how to correct for them. Here I am showing connectivity maps, particularly the connectivity of the amygdala, in 4 subjects collected in 3 different sessions. And you can see some variations in the functional connectivity across the different subjects and also across the different time points. So the question is, how many of these are real neuronal changes? Or could some of these perhaps be just artifacts, that is, just distortions due to non-neuronal differences? And this is a valid question because the way we define functional connectivity is that we look for areas where the signal fluctuates in synchrony. That is, if 2 parts of the brain have their signal go up and down together, we call them functionally connected. But there are a lot of other reasons why 2 parts of the brain could be going up and down in the signal together. Such as physiological noise, heartbeat and respiration, subject motion, or other kinds of scanner instabilities. So let's take a closer look at these different kinds of sources of noise. First, looking at physiological fluctuations. If you look at cardiac fluctuations, in particular looking at the pulsatile nature of the blood, you'll see signal changes with the cardiac frequencies, particularly in pulsatile vessels, like the circle of Willis, as illustrated here. Respiration, that is the actual breathing movement, the chest wall movement actually causes changes in the magnetic field. And these actually cause small shifts of the image. So that's what's shown here in the image on the left, and you can actually see a measurement of the magnetic field changes with fluctuations synchronous with the respiration. In addition, the breathing naturally varies during rest, and this causes changes in the arterial CO2 as reflected by the end-tidal CO2. So in this study from Richard Wise, he looked at the end-tidal CO2 as shown in the trace on the bottom, and compared that to the average gray matter and white matter signal, and you can see striking correlations. And on the right, you can see the areas that show these strong correlations between the end-tidal CO2 and the MRI signal. And the reason for this is that the CO2 is a very potent vasodilator. So if you breathe more shallowly, or if you hold your breath, the CO2 builds up, causes the vessels to dilate, and you get a bold response. You get an increase in the MRI signal. We can also see this just looking at the respiration fluctuations at rest. Here's an example from one of my studies. And you can see the variations in the depth of breathing across the run. If we look at the envelope of that breathing trace, and also divided by the period, and calculate what I call the respiration volume per unit time, here are the signal changes that you would see that are correlated with these respiration volume per time related signal changes. Now, interestingly, at that time, I had a student working with me who was very interested in looking at functional connectivity, in particular, looking at the functional connectivity of the default mode network, having a seat in the posterior cingulate. And in particular, he was interested in seeing whether there were differences in areas that were deactivated at task compared to those that were correlated with the posterior cingulate. And I had just calculated this particular figure that you see here, looking at the respiration-related signal changes during rest. And when I walked over to his cubicle, I saw this figure on his screen showing the connectivity with the posterior cingulate. Striking similarity between these 2 figures. And it made us realize that perhaps some of what we're seeing in this image on the right, the connectivity, was in fact looking at respiration-related changes. What we had expected to see is these areas in blue here from a lexical decision-making task. These are areas indicating the deactivation during this particular cognitively demanding task. On the right, you can see that connectivity with the posterior cingulate showing a lot more extensive connectivity, going down into more of the occipital lobe, further than we had seen with the default mode network deactivations. So one of our thoughts was, well, perhaps this is because the respiration is interfering and causing these additional correlations. And when we had the participants try to keep the respirations as constant as possible, we did see a map that looked a lot more like the default mode network that we saw in those deactivated regions in the previous slide. We also looked at different kinds of corrections that we could do. If you just do the retro-I-core corrections, that it corrects for just the heartbeat and changes at the breathing frequency, really don't see much of an effect of that. Instead, if we remove the that is regress out the average signal from the CSF and from the white matter, we do see a substantial reduction of this correlation outside of the areas that we typically consider part of the default mode network. Another technique that's commonly done to remove sources of noise is global signal regression. At the top, I'm showing you the unthresholded functional connectivity maps with a seed in the posterior cingulate mapping out the default mode network on the left, and on the right, a seed region in the motor cortex. And you can see hotspots in the network, but you also see pretty strong connectivity, or that is correlations with all other parts of gray matter. If you regress out the global signal, that is, if you remove the average signal of the whole brain and regress that out, you end up with a map that looks a lot more focal, that really accentuates these particular networks, as you see here. One of the challenges with doing the global signal regression, however, is that by definition, the global signal contains the signal of interest as well. And so a lot of concern has been whether doing this global signal regression will remove some of the effects of interest. So to give this a bit more context, there was a study that was published showing that the default mode network is anti-correlated with other networks now called task-positive areas. And this made a certain amount of sense. That is, as you engage in a cognitively demanding task, those task-positive areas would increase and the default mode network areas would decrease, and vice versa. However, if you look at the effect of global signal regression, if you don't do any global signal regression, as shown in the bottom, you don't end up with these anti-correlations. You only get these anti-correlations if you regress out the global signal. So one of the concerns was, are these negative signal changes that we see simply a byproduct of performing this global signal regression step, which of course also contains a signal of interest and could distort the results? You can actually mathematically show that after you remove the global signal, the distribution of correlations gets shifted to be centered roughly around 0, and you have to have some negative correlations at the end. So the concern among many researchers is whether this global signal regression step can introduce anti-correlations. However, it's also possible that the global signal regression was reflecting a lot of the noise, and by performing this step, it was removing the noise and uncovering the true anti-correlations that lay beneath it. Unfortunately, at this point in the field, there seem to be two camps. One group of researchers that are very strongly for doing this global signal regression step, saying it's the best way of cleaning up the data and removing these sources of noise. And another group of researchers that are strongly against it, saying you could potentially distort your group results or individual results. I think the better way to think of this controversy really is to try to understand more of what is in the global signal and what does it represent. That is the global signal mostly noise, and in which case we want to remove it to uncover the true neuronal signals underneath? Or does it contain enough neural signals that when we remove it from the data, we're distorting our effects of interest? An alternative to do global signal regression is to regress out the average white matter and the CSF. As illustrated here. Now, there are some that are saying this doesn't completely remove all of the noise and that one should still perform global signal regression, and so the controversy still continues. There are a number of tools out there to correct for physiological noise. I'm just listing them here. I must say I love the acronyms that people come up with, in particular this Apple Core and Pear Core. I'm almost waiting for an orange core to come out so we can compare the Apple Core to the orange core. There's also the fMRIB's ICA-based X-noisifier, one of the more recent techniques for removing various sources of noise that was used in the Human Connectome project. Here I'm listing some of the common pre-processing steps for analyzing data and getting estimates of functional connectivity. These steps are very similar to what you would see for typical task-based fMRI studies. However, I'm just going to point out a few differences, in particular performing physiological noise correction and censoring outlier time points and performing nuisance regression. As it turns out, the functional connectivity estimate is very sensitive to head motion. At the bottom here, you can see a figure from Kuhn and Van Dijk's study, where he looked at the temporal signal to noise with different amounts of motion. And not surprisingly, as the amount of motion increased, the temporal signal to noise decreased. However, look at the axis, look at the scale on this axis, 0.02 to 0.12 millimeters on average. These are really small amounts of movement that can have a significant effect on the temporal signal to noise. At the top, you're seeing the differences in the functional connectivity maps when data points that had a lot of movement have been removed, they call this scrubbed, versus when those data points had not been removed or censored. And I believe the threshold they used for this was 0.2 millimeters. And you can see that it made an effect and improved their ability to detect the connectivity in certain brain regions. In addition, this difference in functional connectivity by censoring versus not censoring was distance dependent. That is, motion tended to increase short-range connections and decrease long-range connections, so that when you censor them, you end up decreasing the short-range connections and increasing the long ones. Now, this is particularly worrisome because at the time, one of the findings in brain development had been that as the brain develops, you see increasing long-range connections and decreasing short-range connections. And this study seemed to suggest that perhaps this is simply because kids move more in the MRI scanner. So my lab has been working on techniques to improve the correction of motion artifacts. For example, using information at the edge voxels that can often represent the motion very well, and we can account for the motion a lot better than just the realignment parameters and the derivatives. In addition, we've come up with a more accurate model of the motion-induced signal change, what we call MOTSIM, that can more accurately reproduce the signal changes induced by the motion than just the motion regressors themselves, which is typically included in order to denoise the data. So here are the different pre-processing steps again, and I wanted to draw your attention to one of these, the nuisance regression step. In the lecture on fMRI data analysis, I had said that ideally what we want to do is we want to include our nuisance parameters together with our ideal regressor, the regressor of interest, in a single model and fit that to the response shown here. If instead we take these nuisance regressors, constant and linear trend, and regress them from the data first, and then if we look at the ideal response and try to fit that to the data, it ends up not fitting very well. The correct thing to do in this case would be to also remove the nuisance parameters from the regressor of interest, and then you would get a good fit. So let's take a look at what happens during resting state fMRI. In this case, we're taking the average signal from let's say the posterior cingulate, and we have some nuisance regressors, for example, a constant, a linear drift, and maybe some motion that we want to account for. We could include all of these together in one model, or if we regress these out first, we get some denoised image. But then what we typically do is we take the average of that seed region, not over the original data, but rather over that denoised data. So in this case, all of these parameters have also been removed from our regressor of interest, and we're okay. We can actually separate those two steps. So in this lecture, we looked at a lot of different sources of noise and the kinds of correction methods that are important to take in order to get good measures of functional connectivity.